I was asked to say something about the geotechnical layer and site response. And so I'm going to do that in a broader context of simulating liquefaction in magnitude 9 Cascadia simulations. I'm going to look at those simulations both in the forward and in the backward direction, and so I'll explain what I mean by that. So my talk is in some sense really an application of simulation data. It probably fits better with the upcoming talks, but in some other sense, it's all about the geotechnical layer. So an outline of my talk that I will keep coming back to. I think the motivations looking at liquefaction in the forward direction are pretty obvious. It's a big problem. There is no infrastructure that is immune to it. And for that reason, it's possible that it can cause more damage than any other effect. In my part of the world, the Cascadia subduction zone, there aren't a lot of regional scale assessments of liquefaction. They tend to rely on a lot of conservative assumptions. That's just what tends to happen at regional scale. So the Department of Homeland Security, for example, put out this report looking at impacts in magnitude 9 events, and they used what I'll call a HAZAS type of approach. And among the conclusions, they said that 2,700 kilometers of roads, 1,800 kilometers of rail, 800 bridges, 8 ports, all probably unavailable due mostly to liquefaction. And this was only looking at Washington-owned infrastructure. I think this outcome is probably like a 5 sigma or 6 sigma type of event. It probably has near zero probability of happening. But for me to say that, of course, really begs some alternative answer. And so that's what we're after here. But I think these types of studies at least point to just how bad the geotechnical response, namely liquefaction, could be. Liquefaction is also interesting backward. So you may know that there are physics-based simulations of magnitude 9 events led by Art Frankel, Aaron Wirth at USGS. We're looking at one realization here, focusing on PGA, which I know simulation people won't want to look at PGA, but it's important for liquefaction. If you just look at Seattle, you'll see PGAs of about 0.1 G. And you don't really have to run the analyses to know that you'd probably have some sporadic liquefaction, but it wouldn't be a major story. Here's another realization though, same magnitude, and now we see PGAs of about 0.3 G. And now the story is totally different, and it's a major part of the outcome. So the question is, well, what can paleoliquefaction tell us about what happened in the last event, which was in 1700? Was that earthquake more like the realization on the left or the one on the right? Or maybe it was like neither. So I'm going to be talking about a couple different types of liquefaction model at different points of my talk. And so I have to just in one slide say something about liquefaction modeling. In my view, there's 3 tiers of model. So there are models that use just geologic or geospatial data. This is freely available, non-invasive, typically data. There's a range of models here, but they're all limited by the fact that you're essentially guessing as to what's under the ground and you're not going into the ground. Tier 2 would be our state of practice models. These use in situ test measurements. They're by far the most common in engineering practice, used to sort of meet the requirements of the building code. And then we have tier 3 constitutive models. These require a lot of parameters, typically some sort of calibration against cyclic lab data, and they can provide some additional spatial and temporal insights. So what we would like to do, ideally, is to use tier 2 or even better yet, tier 3 models. The problem is they require site-specific test data. Therein is the whole problem with regional scale modeling. So the cone penetration test would be our favored test to predict liquefaction. And in the last year or so, we've teamed up with folks at the USGS. We've gone out and done a lot of CPT testing in the region at sites where we're really interested in predictions. But obviously, you just cannot do this sort of testing continuously across a region. So looking forward, our kind of big picture goal, we want to predict liquefaction-induced ground failure for each of these 30 M9 simulations, we want to do that at 400 sites where we have CPT data, and at 10 of these, we have paleoliquefaction studies. Pretty good idea of what happened in 1700. And then number two, we want to make these predictions continuously across the region, and that's where things become challenging and interesting, in my opinion. So with respect to site response, we have the problem that everyone has. Our soil velocity model that underlies these simulations, it's very nice, but it has a minimum VS of 600 meters per second, so something like soft rock. So we need to figure out how do we bridge that structural gap in the velocity structure, and then we need to propagate the motions to the surface. So what kind of data might we look at to do that? Well, sometimes you can go out and measure profiles. I mean, always you can, and sometimes you have that available. So we've gone out and done passive and active profiling at a number of places where we're really interested. Kellogg Island, for example, has a lot of paleoliquefaction evidence. We're just inside the Seattle Basin here, and it's a long way down to 600 meters per second, well over 100 meters, and it's still further, much further at other sites. Number two, you could always have a prediction of VS30. One of the latest models is one that we've trained using machine learning and a large number of geospatial predictors. So traditionally, VS30 models have been based on topographic slope and geology, and those are geospatial predictors. The idea here was, well, why stop with just those? There are dozens of parameters that loosely correlate to the subsurface, and collectively they can train a pretty good model. We also updated the model with regression kriging to bring it in line with reality, and we produced a US national map using this approach. Number three, you could always predict the VS structure with some sort of general velocity model. There's a number of these. I think the most seminal is probably from Shianasamaki. It predicts VS continuously with depth by way of three fitting parameters, A, B, and C, and those are predicted solely from VS30. So Shianasamaki did this in California. Others have since taken the same or similar functional forms, and they've trained on data from the Cascadia subduction zone. If there's a limitation here, it's that this approach says, well, if it has the same VS30, it has the same VS versus depth structure. And that's obviously not the case. And so that's a kind of a clear area where I think people are trying to improve upon things. Number four, sometimes you have CPT data. And there are correlations between CPT and VS. And some of those correlations are region specific. And so you could use that. So what we've done in our work, if we don't have site-specific profiles, is first to take that VS30 prediction that I mentioned that's anchored to reality, and then to predict the rest of the structure using this region-specific model that's essentially following from Shianasamaki. When we have CPT data, we ensemble a number of different correlations, and then for predicting VS, and we then use that CPT data to update the regional model. So we re-optimize the model. With respect to site response, we're using Seismosoil, really nice piece of software from Asamaki and Shi, using their hybrid hyperbolic soil model, wherein the model properties are estimated directly from the VS structure. So obviously, the more soil-specific information you could bring in, the better this would be. But this is what you might be resigned to do at regional scale. We did both equivalent linear analyses with frequency-dependent soil properties and true nonlinear analyses. So if we look at a comparison between the two methodologies, not surprisingly, they start to differ quite a lot at large strain. That's not unexpected at all. And in particular, the EQL FD analyses give larger PGAs than the nonlinear analyses. Now, I think if you look at the literature, look at studies looking at downhole array data, it's not that there's really a consensus as to what type of approach you should use. At least that's my take. I think like most things, it depends a lot on the details. What frequencies do you care about? What soil model are you using? It's unclear really which you should adopt, but we've adopted the nonlinear results in our work. I will say that the consequences of this difference, to some degree, they're mitigated by the fact that they occur when the shaking is very strong. And so whether you have a PGA of, say, 0.6 or 1.6, from the standpoint of liquefaction, your expectation is not going to be that much different at those levels of shaking. So looking at the discrete predictions, where we have CPT data, you may know that there's a lot of disagreement among liquefaction modelers. And so we've ensembled 18 different state of practice models. We have 6 triggering models, and those results then go into 3 different manifestation models. For example, something like the liquefaction potential index. The 18 models here, there are fragility functions conditioned upon these models that are trained on global observations. So what we're ultimately predicting is the probability of liquefaction surface manifestation. And when I say surface manifestation, I'm talking about liquefaction ejecta or ground deformation, which indicates instability, reduced bearing capacity. It's basically a very effective and practical proxy of damage potential for most types of infrastructure. So on the right here, we're looking at the median probabilities of liquefaction manifestation. And if I were just to draw some kind of general observations, well, the probability exceeds 60% at most of our study sites in Vancouver and 40% at most of the study sites in Seattle and Portland. Most of the coastal sample sites do not contain liquefaction susceptible soils. The soils tend to be too plastic in this sort of coastal estuary environment. Of course, they could exist at other locations without samples. The scale is just immense here. I think that's obviously the story of magnitude 9 earthquakes. We're looking at liquefaction from California into Canada and as far east as conceivably the crest of the Cascade Range. So I think it's fair to say that liquefaction could be a major storyline in a Cascadia M9 earthquake. Now, we could zoom in to different places, talk about the best case and worst case outcomes. I don't think I have time to do that. And so I'm just going to continue by saying that the discrete predictions are useful, but obviously the hard part and where we want to get is to continuous predictions. Before I go there, let me briefly say something about looking backward. So the idea here, having just made these forward predictions, is to look at the paleoliquefaction data from 1700 and to see if it fits any one of these 30 simulations better. In other words, can we constrain the ground motions in the last earthquake to any degree? So we did this using 10 paleoliquefaction study sites, and those are mapped here, all of these named places. And these are places where we have a pretty good guess as to whether there is or isn't liquefaction from 1700. Of course, there's uncertainty there, and we've tried to capture that uncertainty by assigning each site this observational uncertainty. So we're looking at how extensive is the search for evidence, how many features are there, how much dating is there, how tight are the date constraints, do they point to 1700 plus or minus 5 years or plus or minus 50 years, for example. So there's a lot of details that I'm passing over here. I think the most notable outcome is that so we calculate the likelihood of each simulation to produce this set of field observations. And notably, even the best fitting simulation doesn't fit the evidence very well. So the simulations suggest that liquefaction should be pretty common throughout the Puget Lowlands, this area between Seattle and Vancouver, and yet there is no obvious or apparent or proposed evidence from 1700. So why do we have that difference? Well, it could be that there's just a lot of evidence that people haven't found. It is rather difficult, after all, to find it. That's possible. It could be that our site response is totally wrong. It could be that our liquefaction models are wrong. I don't think that's the case, but it cannot be ruled out. Number three, well, maybe the 1700 motions were less than expected from these simulations. And if that's true, well, why? Was 1700 not magnitude 9? Was it a little bit less? Was it a lot less? We don't know, but there's a lot of interesting possibilities to consider when you look backward, having generated these physics-based simulations. So finally, continuous predictions, the challenging part. So what we've proposed here is a mechanics-informed machine learning approach where we anchor to in-situ test data in the field. This is work that's ongoing in the US, but we've trialed the approach in New Zealand, and so I'll show you what it looks like there. I'll explain this in 3 simple steps. So step 1 is to get all of the CPTs that you can in the world and to subject them to a wide range of ground motions. For each, you would predict the liquefaction response using our trusted state of practice models. So for example, you would generate LPI versus PGA values. You would then fit a functional form to that response, something like this that has 2 parameters A and B that are effectively trying to capture the liquefaction hazard at a site. How quickly does it rise, if at all, as the ground motions increase? Step 2 is to train machine learning models to predict A and B using a lot of geospatial parameters. This is freely available information that has some loose correlation to the subsurface conditions. Now, 2 examples would be depth to groundwater and depth to bedrock. If you predict liquefaction with these 2 parameters, your predictions will be terrible. But what if you go and get dozens more parameters? I won't read all of these things, but parameters that describe the geomorphology, the topology, the geology, the hydrology of your location without going into the subsurface. Well, altogether, these can make pretty effective models. So we're looking here at forward predictions of those A and B parameters for all of New Zealand. So where they're high, the liquefaction hazard is high. Now with this approach, you can predict ground failure very rapidly because A and B, when convolved with ground motion information, predicts something like the liquefaction potential index instantly. And when you combine that with an existing fragility function, you can predict the probability of ground failure very easily because all of the calculations are essentially pre-computed and stored by way of these parameter maps. There's actually a 3rd step just before that, which is we update the machine learning with regression kriging in this case. So we are predicting A and B with machine learning, but then there are places where we know A and B because we know it from the geotechnical data and models. So this updating anchors us to reality and reduces our uncertainty. So the more geotechnical data that we have, the better. The machine learning models get better. And then we also have better anchorage to better models in the field. And so you can see on the right how the machine learning predictions are updated locally when you have better data and better models. So to close, looking forward, the discrete predictions seem to say that liquefaction could be a big storyline in magnitude 9 Cascadia earthquakes, but the continuous predictions, the thing that really everyone is after here, we think we have an interesting approach to doing that, but we're working on it in the US and globally. Looking backward, it seems like possibly the motions in 1700 were less, at least less than these M9 simulations, so there's some interesting possibilities to discuss. And then more broadly, I think what I would want to convey through my talk is that machine learning and geospatial parameters can be quite effective at predicting subsurface conditions and traits and responses, be it VS30, the VS versus depth structure, be it liquefaction response. Possibly you can think of other applications as well. So with that, I'll stop and just briefly acknowledge other people who have contributed to this on my way out. So thank you.